revolution. So this is a solid of revolution. And as I mentioned for this whole chapter, we're doing volumes, and we're going to do different ways of looking at volumes. And this kind of volume that we first did was stacking shapes. This one is finding a solid of revolution and then finding the volume of this solid of revolution. So part of the start, first of all, is visualizing the picture, and then from that picture, can we get methods to dissect and get the volume? So we're going to practice, first of all, visualizing. I always like to have us practice visualizing first. So suppose I have two functions, x equals 4 and y equals 8, and I just want to focus in the upper quadrant 1, okay? So I want to take the region that's bounded by y equals 8, x equals 4, x equals 0, and y equals 0. So I have this region right here in quadrant 1 that I want to look at. And now, I want to do something. I want to take a region in the plane and I want to revolve it around a line and create what's called a solid of revolution. So we're going to start pretty simple here, okay? I want to take this rectangle, and if you can picture this rectangle, so I have a rectangle, and this will be my axis of rotation. So I've got an axis of rotation, I have a rectangle. Picture taking this rectangle and revolving it around the y-axis. Well, okay, Tina, like this, revolving it around the y-axis. Are you with me? Oh, I got a better picture. Hang on, because I just got dizzy. Okay, hang on one sec. So do this. Let's do this. Let's revolve right here, like that. Right? Go back and revolve. Is there a video? I have a video. I know I have a video here. Ah, there we go. Right there, Wikipedia. Thank you, Wikipedia. Make him play. Why aren't you playing? Oh, you're not playing. You guys can picture what's going on, though, right? So where's my revolving door? Oh, I thought there was a video. There's my video. Ah, there's my video. That way I don't have to spin around. Can you picture taking a rectangle and revolving around an axis, a y-axis? What shape gets created? I'm creating a cylinder. In fact, what I'm creating is that solid cylinder space in there, right? Filled with water or air or whatever. So going back to our shape right here, I want to create a cylinder. So if I take this region and I revolve around the y-axis, the shape I get is a cylinder. And sometimes, so it's easy when it's just a square or a rectangle, but it gets more complicated when it's other shapes. But one trick to help people see this visually in 3 dimensions is to take and mirror image that around your axis of rotation. Oh, I just said something. I'm going to write this down. If I'm going around the y-axis becomes what is called the axis of rotation. And the solid created takes this shape and revolves it 360 degrees around. So sometimes one way to kind of visualize that shape is to draw the mirror image, and then at the top just put like this little circle, like this ellipse thing to represent, to say, okay, here's my shape. I'm going about the y-axis, but it's going to be all the way around 360. So my result is going to be this cylinder right here. So the resulting shape is called the solid of revolution. And our job, what we're going to be doing in a minute, is dissecting and figuring out what are all these volumes of these different shapes that we're making, okay, using different methods. But before, again, we do that, I want you to keep going. I want you to do some more envisioning. And let's take that same rectangle. But instead of going about the y-axis, what happens if I was to go about the line x equals -3? So what if x equals -3 now served as my axis of rotation, and I go around it 360 degrees? What is the resulting shape? Can you draw it? And then down here, I'm going to draw a triangle. Send this about the y-axis. So the y-axis will act as my axis of rotation. Here, x equals -3 is my axis of rotation. And the last one, I'm going to take that same triangle, but this time, instead of going about the y-axis, I actually want to send it this way about the x-axis. So I want to go about the x-axis. So the x-axis will become my axis of rotation. So I want to know what shapes, what three-dimensional solids erupt, are transformed, or are created by taking those shapes and revolving around those individual axis of rotations, okay? So I'll take a moment and we're going to... So this first one, let's see if you're getting what I'm getting. So on this first one, if you brought it over, you kind of would get something like this. And it would go like this. And we would come together. And so I think the shape here, see if you guys got this shape. So the axis, and then you have this thing, and it comes around, and it goes around. So you get this like three-dimensional shape that looks like this. I don't know how you would describe it. It's like a cylinder with a hole. That's how I would describe that one. Like a cylinder with a hole down the middle. Like a disc, kind of like a disc, kind of like this. Somebody said, if you turn it on the side, it looks like it's like a speed tire, like a tire, like in the cars, like how they drew their tires. I don't know if you can see it that way, but it's like a cylinder in a cylinder. The second one, what'd you guys get on this one over here? What did this guy become? This guy became like a cone, didn't it? It became like a cone. But we got an entirely different shape when we went around the x-axis. When you went around the x-axis, you actually got this, it looks like a cylinder, but that's kind of exaggerated. In fact, it's not that tall, is it? It's a lot shorter. So it's a fatter thing here. But it's kind of like a bowl thing. I think of is we had these things where I used to teach. They had an astronomy lab. What do you call those places where you go see the stars?
Conservatory?
A what?
Conservatory?
Like a conservatory, kind of like. Is there another word for it?
Planetarium.
A what?
Planetarium.
Like a planetarium, a conservatory, like a so in this planetarium conservatory, it was like a black hole. So like you took a coin and it went down. And that's what I think of, like a whirlpool, like going, anyways, whatever. Doesn't matter. There, does everybody see? So depending on what axis you go around, you get a different shape. Okay, so our job now is to take these solids and find their volumes. And one way of doing it, and in this chapter we do it an easy way, I think it's the easy way, which is we take these shapes and we cut them perpendicular to the axis of rotation. So if I was to take this shape right here and cut it perpendicular to the axis of rotation, cut it, and then take out a slice, what would that be? What would that be? If I was to cut it and pull out that slice. And is it the same as if I was to cut this and take the slice out? What do you think? So or sometimes it's hard to envision on the bottom. Just take a slice off the top. Just take a slice right off the top. What am I getting?
Circle.
I'm getting a circle, aren't I? Like if I just take a slice right off the top, I'm getting a circle. Or in fact, I get what's called a disc. And so what we are going to start doing is use the disc method, which is we are going to, just like we did stack shapes, we're going to stack discs. And that's going to give us the volume. If I was to cut right off the top on this kind of a shape, what would I pull off? I'd pull off something, it's like a hoop. We call it a washer. So we pull off washers. So again, when we cut this way perpendicular to the axis of rotation, we create this stack of washers, and we add up the volumes for each of those, or add up the areas for each of those. But that gives us what's called disk method and washer method, and so rather than giving you a formula, I'm just going to go right ahead and we're going to try this problem, and then we'll talk through it. So let's do this guy right here. Let's create a solid of revolution by revolving the region bounded by y equals square root of x equals 9, y equals 0, about the x-axis. So the first job is, what kind of shape erupts? And then, how do I get its volume? It's a little different than stacking shapes. It's just slightly different than stacking shapes. So I have y equals square root of x equals 9, y equals 0, and I want to go about my x-axis. First job is to vision or get a picture of what exactly is it that I'm trying to revolve. And so let me see. 1 maps to 1, 9 maps to 3. And so I'm just going to wander and make sure everybody's getting the shape first, the region. The key on this, one method is to cut perpendicular to your axis of rotation. The other one is parallel, but we're going to start by cutting perpendicular to our axis of rotation. So the first thing I want to make sure we have is we have exactly what's going on. We have y equals square root of x. We have x equals 9. We have y equals 0. The very first step is to make sure you have the right region. And then the second step is to make sure you know what axis you're going around. So in this case, we're going about the x-axis. So that makes the x-axis my solid of my axis of rotation. So this is my axis of rotation. Is the x-axis. And when I revolve that around, I get this shape that looks like this. I have this kind of bullet shape that looks like this. Bowl shape, bottom of an acorn, however you can picture it. And so what I'm doing when I get the volume is I cut. So we will cut perpendicular to the axis of rotation, which in our case means we're cutting perpendicular to the x-axis. And we will, when we make that cut, pull off a disc. And this disc is a perfect circle because we're going all the way around, right, 360 degrees. So it is a perfect circle. And so we know the area of a disc is pi r squared. And so when we go to add up all these discs, because that's what we're going to do, just like we added up equilateral triangles or squares, we're just adding up all these discs. We know we need to use this formula. Okay, so let me just set this up to get us started here. So if we mimic what we did last time, to get the volume, we add up a bunch of shapes. And in this case, we're adding up discs. And our disc formula is pi r squared. Because we're cutting perpendicular to the x-axis, that means we're going to be adding them up along the x-axis, right? So we're going to be integrating with respect to x. So we need to make sure we integrate with respect to x. What limits do you think go on there, Arden?
0 to 9.
0 to 9. Beautiful. So we got 0 to 9. Now, here's the tricky part, right, is figuring, not that. The tricky part is figuring out what is my radius. This is my axis of rotation. And the radius goes from the center, which is my axis of rotation, around. And so if I'm drawing a picture, here's my radius, right? You guys got a radius right there, right? So what is my radius for this problem? Yeah, Noah?
Top minus bottom.
It is.
Square root of x.
Beautiful. It's top minus bottom. So square root of x minus 0, which is just square root of x. Do you guys see that your radius for this problem, my radius is my top function minus the bottom. So my radius is just square root of x. Beautiful, beautiful, beautiful. So we're going to get the volume. We're going to integrate from 0 to 9 pi times my radius, which is square root of x squared dx. That's it. That's all we have to do. That's it. See, it's so easy. I love the disc method. It's actually pretty simple. I think students get it, but then when we get some holes and we start going around other places and then we start introducing another method, it gets all confusing. But for now, we can be nice and happy. I think it's pretty straightforward here. So, are you guys getting 81 pi over 2 cubic units? See if you guys are getting what I'm getting on this. 81 pi over 2 cubic units. If I did that right, I might have did that wrong, but I'm going to slow down and stop and take questions. We'll say in your notes, so I will put this because I'm taping this for other people. In our notes, if you go online, you can find notes that pertain to this, and you see a beautiful picture that talks about the disc method. In the disc method picture, they use f of x as your function, but I always like to use r's. So it would be pi r squared, but they use f of x. This is assuming that you go about the x-axis to make this work. If we go about the y-axis, then we're cutting perpendicular to the y-axis, so we'll have to integrate with respect to y instead. But it's really nice. This picture kind of shows you when you cut, you're getting these discs, and we want to add up all these discs together when we integrate. So that's how we're getting our volume. So let's do more. So we'll do this problem, and then we'll do one more after this. But let's start with this one. This one, we want to go about the y-axis. So I think you're going to discover, well, I'll let you discover this. So on this problem, we're looking for the region that's bounded by y equals x cubed. We did one with x cubed already, so we kind of know what he looks like. Y equals 8, and x equals 0. I think that'll put us only up in the first coordinate, in the quadrant 1, in the quadrant 1 with this, when we look at these three curves. And then we want to take this thing, this region, and we want to rotate it about the y-axis, okay? So we want to take this guy and we want to rotate it about the y-axis, alrighty? So that's what we want to try. So we want to take this and we want to rotate this about the y-axis. And our first step is draw a picture. To me, I always draw the picture first so I can visualize and see what my curves are. I'm going to wander. That way, if you guys have any questions, you can ask, okay? So let me just make sure I'm getting the same picture as everybody. So we're going to go y equals x cubed. 2, 3, 4, 5, 6. Nope, wrong. Let's try this again. Make it bigger. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. 2 goes to 8. 1 goes to 1. Y equals x cubed does this. And y equals 8 does this. And x equals 0 does this. And so it's this part in here. So it's kind of like what we did, because it's going to give us kind of a similar shape, unfortunately, but that's okay. Y-axis. As I swoop around the y-axis, I'm getting this long bowl kind of shape. Alrighty. So when I cut, though, I want to always, for this method, we will be cutting parallel to an axis pretty soon. But for now, I'm cutting perpendicular to my axis of rotation. And so when I cut perpendicular to my axis of rotation, you can see it. You can see it right at the top. What we're pulling off is a disc. We're pulling off a disc, hence the name disc method. And then we're going to add up all those discs. But we're going to stack them along the y-axis this time. So first of all, you have to make sure that you have y limits, right? Because now we're stacking them along the y-axis. So our limits, what'd you get as limits? Did you get 0 to 8? I think I get 0 to 8. Did you all get 0 to 8 on your limits this time? So we're stacking along the y-axis, so we're going to go 0 to 8. So, and then we have this radius, which is going to be a horizontal movement this time, right? It's a horizontal movement from the axis of rotation if I see my disk. So this is my radius this time. Oh, shoot. But the problem is I have y equal x cubed, but I'm integrating with respect to y. So did you guys all solve for x and get the cubed root of y? Oh, we got another cubed root of y again. Okay, good. So this is going to be the volume using the disk method is the integral from 0 to 8 pi times the cubed root of y squared dy. And that was y to the root always goes in the bottom. So y to the 2/3 because I have a cubed root. And then I add 1 to my exponents when I'm integrating. So that's y to the 5/3 with a 3/5 in front. 0 to 8. And if I want to calculate it out, let's see if you guys agree with me. 8 to the 5/3 is the same thing as the cubed root of 8. I think that's the cubed root of 8 to the 5th power. Ay, 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 ay. What's that? 2 to the 5th? Which is 32. 32 times 3 is 96. I think that's what I get as my volume for this one. 96 over 5 pi cubic units. Sweet, sweet, sweet. Questions? Let's do this one. This will be my last one for the day. Alrighty, and because I think everybody's tired. It's a Friday afternoon, 3 o'clock in the afternoon. This is our last one. Y equals e to the x. Do you remember what he looks like? Y equals 0. X equals 0. Oh, we should do a sine or cosine. Nah, all right, we'll do this one. Okay, y equals e to the x. When nobody's like, no, Tina, we're done. It's a Friday afternoon. Do not need sines and cosines. Y equals e to the x, y equals 0, x equals 0, x equals 5, about the x-axis. What kind of shape erupts? What does it look like? And what is the volume? First of all, let's make sure everybody's got e to the x. X equals 5. Oh my God, this is huge. Hang on, Tina. That's like a huge shape. E to the 5th? That's like almost 90 something, isn't it? Like, oh yeah, it's huge. All right, so we're just going to pretend like we're way up here at e to the 5th, which is really, really high up. Because if x equals 5, e to the 5th is way super high. Undo. Yeah, and we're taking this shape and we're going to send it around the x-axis, which actually, now that I think about it, is giving me more of a big, like almost like a symbol. If I think about, it's almost like a symbol, like, you know, the symbols that you smack, or the eardrum or something, I think. Is that the piece we're talking that we're going to rotate? Hang on here. So hang on, I'm going to come right there and I'm going to see what you're saying. So let me just make sure. And then we have x equals 0, x equals 5, y equals 0. So I think it's this area in here. Is that what I'm looking at? I think so. I think it's this area in here. I think that's the area I'm looking at. And I'm going about the x-axis. So I'm getting this big cymbal clashing, or a big trombone, right? The entrance of a big, huge trombone. You get it? Oh, yes, you did. Oh, my God, you guys are so good. Can I just tell you, I love your class. You guys are just amazing. Very, very nice. Okay, good. So let's see. So to get the volume, first things first, when we cut it perpendicular to the axis of rotation, so we cut perpendicular to the axis of rotation. That means we're cutting perpendicular to the x-axis. Means we're stacking them along the x-axis. So, Jake, what did you put as your limit? 0 to 5. So we're going 0 to 5 along the x-axis. And then we're putting circles in there. Pi r squared. So each time we put a circle, but the circle has a radius, and that radius is just the distance from the axis of rotation to the curve. And so did you get your radius, Jake, to be e to the x minus 0?
Yes.
Yep, you did. Awesome. So that means we're taking a volume. 0 to 5 pi times e to the x squared dx. Beautiful. And Noah, what did you say when you take e to the x squared? What do you do with those powers? You multiply them. Did everybody multiply them and get e to the 2x dx? Ah, so nice. Good. You guys are so good. And then we have to do the antiderivative. So this is when you have this linear, right? We have this linear coefficient in there that we have to remember we do. So when you did the antiderivative, did you get pi over 2 e to the 2x? I think you did, Jake, didn't you?
Yes.
Yep. And then you plugged in. So then we plugged in. So then we plugged in a 5. Oh my gosh, Tina. So we plugged in a 5 and we got e to the 10. And we plugged in a 0 and we got e to the 0. And you have to be really careful when you do this on web work, because e to the 0 is in fact a number. It's not 0. And so many people will just go 0 and then they'll get it wrong on web work and they'll be bashing their brains thinking they don't understand. But e to the 0 is 1. And so make sure you put that 1 in there when you're doing this on web work. I love it. I love it. How are we? Alex, you got it okay? You get it good? Arden? Ella, I went fast. You good? You guys good? Everybody good? Any questions? I think you guys have the disk method down, no problem. I think when it gets more complicated is, number one, if we were to have a shape that might have multiple functions to rotate. Number two, if we were to take this and start rotating it now around the y-axis, now we get a hole, so we have to talk about what we do when we get a hole in there, okay? Or if we go and take this around the line 5, oh man, what would we do with that, right? So if we instead took this shape and went around the line x equals 5, we get a solid shape, but what is that volume? So those are all questions to talk about and think about. But we'll do that next week because I know I have a whole lot of students out, so I don't want to go too far too fast. So on Monday, we'll talk about the washer. We'll review disk real fast. We'll do washer method, and then we'll talk about going about different lines on Monday.